Welcome everybody to Calculus BC. In today's episode, we're going to be discussing chapter 9.8, which is the power series. Now, the power series, what it does, unlike the series we have been dealing with, which only have been having numbers inside the summations, the power series is going to take a bit of a different turn. What it's going to introduce is it's going to introduce the notion of variables inside the summation. So whereas we used to have things like this, like the sum from n equals 1 to infinity of, say, like 1/2 to the n, right? We would see this as, say, 1/2 plus 1/4 plus 1/8 plus dot, dot, dot. So this was our standard operating series up until now. This is a geometric series. But what's going to happen now is the power series, the notion of power series. I'm going to give to you something that looks kind of like this now, where from n equals, say, 0 to infinity of, say, x to the n. And we're going to be asked to expand this thing. Well, what's going to expand this out? Well, what we've got is we've got 1, right, as our first term. If I plug in 0, I've got x as my second term, then x squared, x cubed, plus dot, dot, dot. And I think you can kind of see where that pattern is going to be going. Now, what these two series have in common is that they're both geometric in nature, right? Which means just like this one here, who, because the absolute value of 1/2 is less than 1, right? Our r, right? R was equal to 1/2. This one we actually could find the sum for, right? We could say that s was equal to the first term, so in this case 1/2 over 1 minus r. And we would eventually be able to find out this sum. This would end up becoming 1. This guy here is the exact same thing. What I've got is s is equal to a sub 1, which is going to be 1, over 1 minus, and in this case, my ratio here is x. So I'm going to say 1 over 1 minus x. Now, this summation is dependent, right? Like this summation right here will ultimately turn into this, but it is dependent upon the notion that the absolute value of r is less than 1. In the context of this problem, that would mean the absolute value of x would have to be less than 1. So that is where this summation would be true. So the power series, ultimately, what it does, the power series defined, is what it does is it takes our standard operating series and starts inputting variables into there. Now, there's a reason why they're doing this, and I'll show it to you instinctually in this lesson, but we will define it for sure more explicitly in upcoming videos. But what it says, the power series about what the power series says is, if we have the sum from, say, n equals 0 to infinity of, say, c sub n, right? So that would be like just some constant times x minus a to the n. That ends up being c sub 0 plus c sub 1, and then times x minus a to the 1, plus c sub 2 times x minus a squared, plus c sub 3 times x minus a cubed, plus dot, dot, dot. Now, if you're wondering why why the c sub 0 doesn't get an x minus a, well, it kind of does, right? Because this is technically x minus a to the 0. Ultimately, that's going to end up becoming 1, so we don't really need to be worried about it. So that's ultimately what a power series is defined. Now, let's go ahead and take a look at an example. And what I'm going to have us all do here is we're going to be given a series. So the series starting from, say, n equals 0 to infinity. Let's see. X to the n over n factorial. So what we're going to do is we're actually going to just expand out the first few partial sums. So we're going to say expand, let's say the first 4 partial sums. The first 4 partial sums. So let's see here. What does that mean? S sub 0. Well, again, what does that mean? It just means that I'm going to plug in So let's take a look at this summation right here. It's going to be the sum from n equals 0 to infinity of x to the n over n factorial. Let's go and just expand out some terms here, because what I'm going to have us do in a few seconds here is we're going to list a bunch of partial sums. So if I was to just expand, say, the first, say, 4 or 5 terms here, what I'd end up with is if I let n equal 0, right, I'd have x to the 0, which is 1 up top, over 0 factorial, which is 1 on bottom. If I let n equal 1, I'm going to have x to the 1 over 1 factorial. If I let n equal 2, what I have is x squared over 2 factorial. And I think we see what is happening here. X cubed over 3 factorial, x to the 4th over 4 factorial, x to the 5th over 5 factorial. And I don't see any kind of alternation going on. This is not like an alternating series. I feel like these are all just going to be added up together. And that's, again, n equals 3, n equals 4, n equals 5. So these are my first 6 terms right here. But what I'm going to have us do now is I'm going to have us do a partial sum expansion here. So we're going to find out just the first few partial sums. So if I said s sub 0, that would be the sum of the first, say, 0th terms, right? That would be 1, right? Just 1. S sub 1 would be, again, the sum of the first and second term. So in this case, the 0th and the first term. So 1 plus x. S sub 2, I think you kind of see where this is going. X plus x squared over 2 factorial. I'll move it over to here. S sub 3 is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial. S sub 4 is going to be 1 plus x plus, it's just going to be, the same line as above, right? Except adding on that next piece here. So 1 plus x, oops, sorry, I forgot about that guy. X to the 4th over 4 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, plus x to the 5th over 5 factorial. So ultimately, you're asking a very legitimate question. It's like, well, what do we care about this? And so what I'm going to have us do now is I'm going to have us go to either a graphing calculator or a graphing program. I'm going to go to Desmos here, and I'm going to go and graph all of these partial sums individually. And then I'm going to ultimately plug the summation into Desmos to find out what's going to happen as n approaches that infinite value here. So let's go and go to Desmos. And so as you guys see, I already have the first 4 partial sums lined up. I just didn't want to type them in and waste all that time, so hopefully that makes sense. So I'm going to go ahead and do that first partial sum, which is 1, right? 1, I get this red line going straight across. Nothing too special about him. If I highlight the 1 plus x, now I get something linear, which makes sense. Then I get something quadratic on the next line here, and it should make sense, right? I'm getting more and more terms here. As I go forward, my exponents are getting higher. A quadratic, it's nothing too special. Again, nothing we haven't seen from integrated 2. Then the next one's going to be a cubic function, right? A third power function, which is going to look like that. So we should predictably see this behavior here. Now, ultimately, I'm sure you're wondering, so where is this thing even going? Like, why do I even care? It just looks like, more and more complicated polynomials. Well, what I'm going to do here is I hope you have this image in your head right here, or if you've drawn this image somehow, hopefully that makes sense, because I'm going to go and get rid of them. And now I'm going to go back to the summation, because I don't want to keep on typing in a bunch of values. Now I'm going to type in 5. Another 5th power polynomial, 6, and I hope you guys can start to imagine what that's going to look like, right? The 5th one would be plus an x to the 5th over 5 factorial. This would be at the end plus an x to the 6th over 6 factorial, 7, and then 8, and then 9, and then 10, and more it's starting to look more and more like a flat bottom right around here. The bottom is starting to flatten out the bigger I get. The larger I get, the larger I get, the flatter this becomes. I think I kind of spoiled the ending for you. But if I end up getting to the 100th power, what's going to happen is this guy is going to look more and more like this. And if I let n equal 1,000, it's going to look even more like that, right? And I think it's just trying to load up. So the 1,000 didn't cause that to disappear. I think it's just loading up. Because what happens is that this program tends to slow down the more and more values you put in. So 1,000 seems to be a lot. But I think at the end of the day, even at 100 values, it's starting to become more and more clear as to what this thing is going to look like. And so what we can do is we can conclude that as n approaches infinity, right? So as n approaches infinity, right? This guy here, this guy's summation, x to the n over n factorial, will look exponential. Now, what type of exponential will it look like? We can probably take a guess as to what it's going to look like. It's probably the most quintessential exponential you can think of. Does it, in fact, become this? Well, from here, I'm going to have us kind of store this here. We don't really know that to be true for sure. But in a couple of future videos, I'm going to show that it will either become our good old buddy e to the x, or it won't. It'll become something totally different. And it's possible I've been lying to you this whole time. But we'll save that for a couple more videos. I'll leave you on a cliffhanger right there. Let's go ahead and move to a different example, and then I will, we'll do some more power series messing around with this stuff. All right, in this next example here, we're going to look at this power series here. First thing to note about it, it is alternating, right? So this one's going to be a little different than the last one. And so from here, what we're going to do is we're going to expand. We're going to expand the first 5 terms, and then we're going to check it out in the calculator. Check in calculator. So if you want, take a second, pause this thing and try and expand the first few terms on your own, but what this thing's going to end up turning into is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. So that's my first 5 terms. So let's go and check it out in the calculator. All right, and here we are. What I did for this one here is I actually just put in the summation. That way we wouldn't have to keep on typing in all the factorials and all the different fractions. And so what I've done here is I've done the summation from n equals 0 to 0. So this is our first term. This is that x term that we have, right? This is the first partial sum. If I suddenly let this guy become a 1, right, I end up getting this weird looking upside down x to the 3rd bit, which makes sense because it's x minus x to the 3rd over 3 factorial. If I let x equal 2, then I have this, or if I let n equal 2, then I have like this weirder looking, it looks like probably a 5th power polynomial, right? Because now we're at that x to the 5th term. If I let this thing become 3, now it becomes more like that. And as you can see, there is this alternating behavior between the two, right? If I let x equal 4, then I end up with this, a little bit more wavy. Right, 4. If I let n equal 4, then I get to an x to the 7th function. 5, it looks more like this. If I do 6, it's going to look ultimately like that. And at the end of the day, if I just keep letting n get larger and larger, notice what's happening with the graph. It's expanding to the left and right. It's getting more wavy as we keep going on. Of course, the ends start breaking away, but the middle behavior towards the center here, this should start looking a little bit familiar, where we end up with these waves that they just keep on expanding out. And if I went to 100 terms, that might look familiar. We have something that starts in the center, goes all the way up and all the way down and all the way up and all the way down, and we keep on going. And so I want to have just some kind of reasonable prediction as to what's going to happen here. So as n approaches infinity, the sum from n equals 0, the summation of this particular power series here, what does it become? Does it in fact become sine x? Well, again, kind of like that one time we predicted that the previous series would become exponential, I'll kind of leave you guys hanging for a little bit on that one. In the meantime, let's go ahead and do some manipulations with this series that we've just created right here. And so, remember, whenever we create a partial sum series from this series generator, we're really just creating a polynomial, right? We're just creating a polynomial expression. And so what I'm going to do is I'm going to go ahead and derive that polynomial expression. Now I'm going to go ahead and derive the first few terms here. So it'll be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus ... And again, I'm using more than the first 5 terms, but let's see what happens if I derive this here. I'm going to end up with 3 times 2 here, 5, 4, 3, 2, 1 here, and so on and so forth. Well, what's going to happen if I derive this, guys, I'm going to end up with 1 minus, this 3 will come down and cancel out that 3, giving me x squared over 2 factorial. This 5 comes down and cancels out with that 5, giving me x to the 4th over 4 factorial, plus x to the 6th over 6 factorial, plus x to the 8th over 8 factorial, and so on and so on and so forth. Now, I feel like I just made a mistake right there. That is actually a minus because we're alternating signs. And so now from here, let's go and try and come up with a general term for this thing. So if I just start off with n equaling 0, if I go to like some value k, well, this is going to be alternating, so I know it's going to be negative 1 to the n. I know that first term is going to be 1, so if I let n go from 0, then I'm good. And then I'm going to have x to the 2n over 2n factorial. Hopefully that makes sense. The slope here is rising up by 2, and then so is the denominator, except it has a factorial attached to it. Now what I'm going to do is I'm actually going to go to back to Desmos, and we're going to see what happens when I plug this into my function here. Now, bear in mind, I have derived something, a polynomial, that is supposed to resemble sine. Well, what am I going to get? I hope you have a prediction, because this is the sequence generator right here. If I look at the 0th term, I get that straight line right there. If I go to say 1 term, I get a parabola. 2 terms is a quartic function. 3 terms, 4 terms, 5 terms, 6, 7, 8, 9, and 100. And what I get is I get something that very much resembles cosine, right? And so from here, we should have had the reasonable expectation that as k goes to infinity, this series from n equals 0 to k of negative 1 to the n times x to the 2n over 2n factorial does in fact approach cosine, or at least a cosine-looking thing. And again, that's just one reason why they resemble each other. In a couple episodes, I am going to go over why they actually are each other when we get to something known as the Taylor series. So hopefully that makes sense. I think I'm going to wrap it up here with this episode. As always, please leave comments or questions in the comments area. I will be back in the next episode with the radius and interval of convergence of the power series. See ya.